Hello guys, today in this class I am going to explain about the fiber optics. Myself, Dr. S.S. Bellad from Department of Physics, Marani Science College for Women. And we'll see what is this fiber optics. So what is the fiber optics? Fiber optics is the branch of physics which deals with the guiding and transmission of light through very fine and thin fibers made of particular glass or plastic. These optical fibers carry light over distances ranging from a few centimeters to hundreds of kilometers. So this is the field of optical fiber optics. Here we are mainly dealing with the guiding of light through very fine and thin fibers, which are called as the optical fibers, and which carries the light for a very long distance without loss of energy. That is very, very important. So how this concept arose is that so this concept of light guiding is evolved due to the invention of this John Tyndall in 1870. In 1870, John Tyndall demonstrated that light propagation can be guided. So here you can see in this experiment, it is a very simple experiment. As water poured out through this part of the first container, Tyndall directed a beam of sunlight at the path of the water. So you are looking at the a container filled with water. Here sunlight is there, and this is the spot of this first container. So as soon as you pour the water into this container, the light comes out, starts flowing out through this spot and falls here. You can also place another container here. So Tyndall, what he did is that he directed a light rays into the opening of this spot. He directed a light ray into the opening of this spot. Then he observed here. Very interestingly, the light ray was guiding here, and it was propagating along with the direction of this water flow. So the light followed a zigzag path inside the curved path of the water, and this idea known as the total reflection is the basic of fiber optics. So here you can see the light is taking the zigzag path inside the water flow, and it is getting reflected back here. So why it gets reflected back here? Because water, the density of water as compared to the air, here air is there, but this is the water. So the density of air is automatically or obviously more than the density of air. So here, when the light is made to propagate through this water, what happens when the light rays hit the interface of this water and air, the refractive index of the two media also going to is also changes, and the light will travel from denser to rarer medium. Water becomes the denser medium and air becomes the rarer medium. And the condition for this phenomena called as the total internal reflection is that the angle of incidence should be greater than the critical angle. I will explain what is this critical angle later. And the light ray should travel from denser medium to rarer medium. So these are the two conditions to be satisfied for the total internal reflection of the light. Both these conditions are satisfied here. So because of that reason, the light is guided, or it takes the multiple reflections inside this water flow, and it propagates along the path of this water, and lastly at the end here it leaks out. So this simple experiment ignited the mind of many researchers, and the people started to work on this phenomenon, and they tried to guide the light wave in a medium. So in this way, the research on guiding the light wave started. So here just these are the important inventions who are very useful for this phenomena of optical fibers and the developments on the optical fibers. And just I will read out these important inventions. These are: in 1873, Maxwell told that the light is propagating in the form of electromagnetic waves. So he formulated the phenomenon or the concept of the electromagnetic waves. And in 1876, Elisha Gray and Alexander Bell invented the telephone in Bell Laboratories, USA, United States of America. And in 1877, first telephone exchange was established. And in 1880, Bell invents a photophone. And in 1888, Hertz confirms electromagnetic waves and relation to the light. So here Maxwell was stated that the light is propagating in the form of an electromagnetic wave. That concept is confirmed by Frank Hertz, in 1888. And in the same year, by the end of 1920, glass rods used for illumination of the light. And in 1897, Raleigh analyzes the waveguide. And in 1909, Marconi radio communication started. Marconi showed that it is possible to communicate via electromagnetic waves, that is the radio communication started. In 1902, Marconi invented the radio detector. And in 1930, Lamb experiments with the silica fiber. Lamb experiment, silica fibers were determined, and when some experiment was done, this was the first fiber discovered in the world, that is in 1930. And in 1931, woven fiberglass are discovered. And during this period of 1936 to 40, communication using a waveguide started. And in the year 1950, the production of fibers started, but with greater losses. The losses observed by the optical fibers were large. In 1960, invention of laser by Maiman was the breakthrough. This was the major breakthrough in optical fiber communication. And in 1968, Nippon Glass Company of Japan produced the optical fiber with the loss of 20 dB per kilometer. And in the 1970, Corning Glass, this is the company of US, Corning Glass Works of US produced fiber with the loss of 20 dB, 20 dB per kilometer. So two companies started to produce the optical fibers. And in 1977, a low loss fiber, it is 0.2 dB per kilometer only. A low loss fiber was produced and optical communication system installed in Chicago, USA. So these are the latest or important developments in the field of optical fiber communication. So here we will understand what is this total internal reflection, and this is the very, very important phenomenon on which this optical fiber communication or the optical fibers works. So when a light ray traveling from an optically denser medium to an optically rarer medium is incident at an angle greater than the critical angle for the two media, the ray is totally reflected back into the denser medium, obeying the laws of reflection. This phenomenon is known as the total internal reflection, and the angle of incidence at which the refracted ray just grazes the surface is called as the critical angle. So I will explain these things with these three diagrams. So you are looking here, these are the two mediums. It is the medium 1 and medium 2. So this is the denser medium and this is the rarer medium. And N1 is the refractive index of this medium, denser medium. And N2 is the refractive index of rarer medium. So rarer medium means that is the medium which is having a low density as compared to other. So it is called as the rarer medium. So this is the normal. This vertical line is the normal to the interface of these two. And this red colored arrow mark indicates the direction of incident light. This is the direction of incident light. And so this I is the angle of incidence and R is the angle of refraction, because these things are always measured with respect to the normal. So angle of incidence is measured with respect to this normal, and this R, angle of refraction, is also measured with respect to this normal. And it is very clear that when this is the angle of incidence, the light refracting into the second medium in this direction. And one more point is observed here is that when the light is moving from denser medium to a rarer medium, it bends away from the normal, or it will go away from the normal. This is the normal. So it is going away from the normal when the light propagates from denser medium to a rarer medium. Suppose if you reverse the thing, that means when the light moves from rarer medium to a denser medium, at that time what happens? The light will bend towards the normal. So this is the normal. The light ray may go somewhere here. So this happens. And now this I, in this case, this I means the angle of incidence is less than the critical angle. So therefore the refraction of light takes place. So the light is propagating in this direction. And here you can see now the angle of incidence is made in such a way that the refracted ray just grazes the interface of these two media. So this particular angle of incidence of the light for which the refracted light, for which the refracted light just grazes the surface is called as the critical angle. And in this case, what happens? The angle of incidence is still increased beyond this critical angle. So in this case, now the angle of incidence is greater than the critical angle. So when the angle of incidence is beyond the critical angle, you can see the light is coming out into the denser medium. So the light is coming back to the same medium. So the phenomena observed here is a reflection of light. So here it is a refraction, here also it is a refraction, but here it is the reflection of light. And here the light obeys the laws of reflection also. So at this interface, the light is deviating. The light is deviating into the same medium. And this phenomenon is called as the total internal reflection. So when the light is reflected under this condition, that means when there is a total internal reflection phenomenon, here the loss of energy at the interface is very, very less. That means the loss of energy at the point of incidence is very, very less. So that is why for the faithful propagation of the light inside an optical fiber, the total internal reflection is a very, very necessary condition to be achieved. So that is why in the optical fibers, always the light, the signal or the light is directed into the fiber with an angle greater than the critical angle. So here are some equations. According to Snell's law, for the pair of medium, n1 sine I is equal to n2 sine R. n1 is the refractive index of first medium, and I is the angle of incidence, and n2 is the refractive index of second medium, and R is the refraction, angle of refraction. So for the total internal refraction to be observed, at least I should be equal to C. At least, actually, when I is equal to C, that means when the angle of incidence is equal to the critical angle, the refracted ray grazes the surface. So actually, we need that angle of incidence should be greater than the critical angle. So when I is equal to C, when the angle of incidence is equal to C, the critical angle, for that angle of incidence, the angle of refraction will be 90 degrees. This is very clear in this diagram. You can see here in the middle diagram, this is the angle of incidence, which is equal to the critical angle. The angle of refraction, this is 90 degree. With respect to normal, this is a 90 degree. So the angle of refraction is 90 degree. You can put these two conditions in this equation. So this equation becomes n1 sine C. In the place of I have substituted C. So n1 sine C is equal to n2 sine 90. R is 90 degree. So it is n2 sine 90. As you know, by trigonometry, sine of 90 degree is 1. So this sine 90 becomes 1. So it becomes equal to n2. Or therefore, this n1 sine C is equal to n2, or sine C is equal to n2 by n1, or C is equal to sine inverse of n2 by n1. So this So this C represents the critical angle for a pair of medium. So if we know the refractive index of that pair of medium, we can calculate what is the value of this critical angle. So for angle of incidence greater than the critical angle, the total internal reflection takes place with no losses at the boundary. So here we'll see what is the construction of an optical fiber, how the optical fibers are constructed. You can look at this diagram. This is the it's a real optical fiber, and it is having a inner core which is having more refractive index or more density. So this is a core medium, and this core is surrounded by another medium called as the cladding. So this cladding is there. This cladding is overlapping this core, and these two are further overlapped or further covered by this layer. It is called as the polyurethane jacket, and this is further covered by a plastic cover. It is called as the buffer coating. So this is the construction of an optical fiber, and this is the refractive index profile of an optical fiber. So you can see here, this inner circle is the inner core, and this inner core is surrounded by another material that is called as the cladding. So this is the core and this is the cladding. So these two material, actually core and cladding, are actually made of the same material, and only thing is that they have a slight change in the refractive index. That means the refractive index of core is greater than the refractive index of cladding. And you can see here, suppose if you are sending a ray of light with an angle greater than the critical angle, so that ray of light will propagate through this optical fiber in this way, and it takes multiple hits at the interface of this core and cladding, and it comes back. So in this way, the light is guided to propagate inside the optical fiber only. So an optical fiber is made of mainly two parts. One is the inner cylindrical material made of glass or plastic called the core, and its a thickness or diameter is around 10 to 50 micrometer. The other is the cladding, having a thickness of 125 micrometer, which envelopes the inner core as a concentric cylinder. And the cladding is also made of similar material but of lesser refractive index. So there is a material continuity between core and cladding. That means at the interface, the refractive index of both the materials are not going to change suddenly. Gradually, the refractive index are changing gradually, making a continuity between the two layers. So the cladding is surrounded by a polyurethane jacket which safeguards the fiber against chemical reaction, abrasion, and crushing. So this is how the optical fiber is made of. And many such fibers, each one protected by individual jackets, are grouped to form a cable. A cable consists of 1 to several hundred such fibers. You can look at there. This is a cable. This is an optical cable. This optical cable is consisting of very huge number. Hundreds of optical fibers are bundled into one cable. And optical fiber as a waveguide. So the optical fiber acts as a waveguide. So this too this is the optical fiber, and here sender is there and here receiver is there. So who is the sender? It is the source of light such as a LED, light emitting diode, or laser. Laser source can be used. So the sender means it is a source of light, either as a light emitting diode or laser source is used, and the light is directed into this optical fiber with angle of incidence here greater than the critical angle. And what is this receiver? It is a light detector such as photodiode. So a simple photodiode can be used as a detector and which receives the light. So when light from source enter the fiber with an angle greater than the critical angle, it is continuously undergoes a total internal reflection at the core cladding interface for every time it hits. Thus, light is prevented to escape from the fiber. Hence, it is called fiber waveguide or fiber light guide. So you can look, you can see at this diagram, it is very clear that light is propagating in this way each time hitting this interface of core and cladding. And here the total internal reflection, wherever the light hits the interface of core and cladding, the total internal reflection takes place, and because of that reason light comes back to the core medium, and again, so in this way it propagates, and the loss observed at the interface of core and cladding are very less because of the this phenomena of total internal reflection. So this is, so we seen that an optical fiber acts as a wave guide, and we'll see what are how many types of optical fibers are there. So the curve which represents the variation of refractive index with respect to the radial distance from the axis of the fiber is called the refractive index profile. So on the basis of this, the optical fibers are classified into three categories. So based on this refractive index profile means it is the variation of refractive index along the radial distance from the axis of the fiber is called as the refractive index profile. So based on this refractive index profile, the different types of optical fibers are constructed, and the first type is the step index single mode fiber. Another one is the step index multi-mode fiber, and the third one is the graded index multi-mode fiber. So in the next session, I am going to explain these three. What is the step index single mode fiber? What is the step index multi-mode fiber? How it is constructed? And what is the graded index multi-mode fiber? How it is constructed? Yeah, we are going to discuss in the next class, next session. Thank you for listening.